Okay, so we are going to work an example of solving, we call it a 3x3 system of linear equations, and we're going to do it by hand. Now, it's not hard, but it's very detail oriented, so make sure you have lots of paper and stay calm. Okay, so 3x3, and it gets that name because I have 3 variables and 3 equations, and these happen to all be linear equations, which is good. And you can recognize them as linear because each of the variables is raised to the first power. If you want a picture in your head, if that helps, these all represent planes out in 3 dimensions. So imagine we had 3 sheets of paper out here in the space and how those could interact with each other. Okay, so here's what the goal is. Just like you do elimination when you have 2 equations and 2 unknowns, we're going to follow that method here as well. Yes, you could also do a substitution method and it would work just fine. Here's how we do the elimination method though. I'm going to pick one of the letters to get rid of twice. So when I first saw this system, what I noticed is the y's, right? So the first equation and the second equation have a plus 3y and a minus 3y. So I see that if I add these 2 equations together, I'll get an equation that only has x and y in it. Okay? Or I'm sorry, x and z. That's great. Because now I have an equation that has just 2 variables, and those we've already learned how to solve. So let's go ahead and add these 2 together to get a new equation. So x plus 2x, 3y plus a negative 3y, those go away. 4z plus 2z, and 14 plus 10. Okay. So what I now need is one more equation that only has x's and z's in it. So I have to pick another pair, and it doesn't matter which pair you pick. I have to pick one more pair and get rid of the y again. Okay. So let's take first and third and make the y's go away. So what would we have to do to make that happen? So my first equation still has a 3y, right, positive 3 coefficient. So this equation would need a negative 3 coefficient. Right now it's negative 1. So I'll have a little workspace down here and we'll go ahead and manipulate. So I'm going to multiply this third equation by positive 3. Multiply that third equation by 3, right? And that's my shortcut notation. I just drop the whole equation in parentheses and stick a little 3 out in front. Just reminds me to distribute it over here on the 9. Most students who mess up, they forget the right side of the equation when you're scaling. Okay, so 9x minus 3y plus 3z equals 27. And then the first equation, I'm not going to do anything to. I'll just recopy it though, so it's close by. Okay. And now we're going to add these together. And I'm going to go ahead and I'll just write my result up here under my other 2 equations, or 2 unknowns. So 9x plus x, 10x, y's go away. 3z plus 4z is 7z. Oh dear. And 27 plus 14 looks like 41. Well, now I have 2 equations, 2 unknowns, and that we were solving before. So I need to get the coefficients of one of the letters equal and opposite. Or, oh gosh, look at this, guys. So I have 3, 6, 24. 3 goes into all of those. Let's go ahead and divide that 3 out. So let's divide this whole equation by 3. Because otherwise I had a whole bunch of scaling to do. But look what happens when I multiply it by 1/3. Right? Same thing as dividing it by 3. I'm going to write it down here. So 1/3 times 3x, 1/3 times 6z, 1/3 times 24. Okay. So now I have this system to solve. Let's see. What happens if I multiply the bottom equation by negative 10? Can you see what letter is going to go away? Yep. Okay, so top equation is going to stay the same. 10x plus 7z equals 41. Bottom equation, I'm multiplying the whole thing by negative 10. So I'll get negative 10x minus 20z equals negative 80. And now we're going to add those together and hope for integers. Let's see, my x's go away. I'm going to get a negative 13z equals, oh dear, 80 minus 41. Oh, 39, negative 39. And then divide by negative 13. And we get z equals 3. Yay! We're a third of the way there. Actually, we're more than a third because we've done most of the heavy lifting. Once you have one of your variables' values, you can just work your way back up through your systems, right through your equations to find the other two variables. So here's a relationship I have between x and z and constants. So I know that if z is 3 and I plug that in, that'll tell me x. So here we are looking for x. X plus 2 times z, which we know is now played by 3, equals 8. X plus 6 equals 8. Looks like x is 2. Okay. And so we still need to know what y is. To get y, we have to go all the way back up to one of the original equations where we know x, y, and z. So if I grab the top one, which I know is off your screen, but you can look on your notes. So I have x plus 3y plus 4z, z is 3, and that has to equal 14. Okay, so y is the only thing I still don't know. Let's see, 2 and 12 is 14, so 3y plus 14 equals 14. 3y equals 0, so it looks like y is also 0 when you divide the 3 across. So my solution, you can write it, it's called an ordered triple. And x, y, z, 2, 0, 3. So this is the point in 3 space, in 3 dimensions, where those 3 planes would intersect. Okay? So just to verify what we found, I'm going to go ahead and recopy that system down here. And we're going to check and verify that that ordered triple works in all 3 equations. So we're going to do a check. It has to work. These 3 numbers have to work in each equation. Okay, and we'll just do it mentally. Here we go. 2 plus 0 plus 12 is 14. 2 plus 12 is 14. Yes. 4 minus 0, I better write it down, I guess. 4 minus 0 plus 6 is 10. Yay. Let's see, last one. 2 times 3 is 6, minus 0 plus 3. 6 plus 3 is 9. Yes, it works in all of them.